a set, and we said that it's a kind of a set that you can't measure with the Lebesgue measure. Okay? You can't measure it with the Lebesgue. So we kind of had an example of a non-measurable set. So what I'm going to do now, I'm going to present some of the properties, but without proof. Okay, I mean, if you're interested, you can see it from there. But I would like to just mention them that at least they should stick in your head for once. But I would highly recommend that you should read the proof of them as well. Okay. So in this chapter 4, what we have essentially done, we have said that okay, we kind of we have proved the Caratheodry theorem, which simply says that okay, if you have a collection of subsets, okay, of a given set, and you have some notion of length associated with that, then using that notion of length, you can construct an outer measure, and then you collect.
Then restrict that.
Okay, then if you collect, for example, all those sets which are measurable by that outer measure, okay, and you start measurable sets, then there becomes a sigma-algebra, and if you restrict the outer measure, on that sigma-algebra it becomes a measure actually. Okay, and as an example, we deduced the back measure, the Bedell-Stingy's measure. Okay, and then we also saw that if we compute the back measure of the interval, okay, then it is same as the length of the interval. So this is what we ended, and then afterwards, basically, in the end, we did an example of non-measurable sets. Okay, I would like to mention some of interesting properties, some of interesting consequences of the back measure. For example. So I'm not proving it, okay? So because it's going to suck time actually. But I highly encourage you to read out the proof. Okay? So suppose A is a subset of this interval 0, 1 that is well measured. That is well measured. Okay? And let M be Lebesgue measure. Okay? So Lebesgue measure. Then what the proposition is saying that for each epsilon positive, for a given epsilon positive, I can always find an open set, okay, G, which kind of approximates this Borel measurable set. Okay, so in other words, I can make the measure of the difference of A and the open sets be less than arbitrarily small epsilon actually. So in other words, I can treat Borel sets as, especially this would be very useful in probability, as approximately open sets. They're not exactly open, but they are approximately open sets. So in other words, for given epsilon positive, I can find an open set G, okay, such that if I compute the measure of G minus A, it would be less than epsilon. Okay? So in other words, I can.
Sir, M.
So,
M.
M. Sorry. Lebesgue measure of M, okay, G minus A would be less than epsilon. So in other words, for every epsilon, I can find such an open set. So in other words, I can always find an open set which kind of approximate, the given Borel set taken up to, okay, so up to our satisfaction level actually. So how close you want to make it? So you can always find open set. Okay, this kind of an approximation. Second, Similarly, for given epsilon positive, I can find a closed set such that almost something similar, such that A minus closed set, let's denote that closed set by F. Okay. The measure of A minus F is less than F. Okay.
Here it is subset of A.
It's
If
F, it's not necessarily a subset of F. It's not necessarily a subset of F, but the difference would be almost
say yes alone.
pretty same. Okay. So I think these are two very interesting consequences. I'm not getting into the proof, but the statements are self-evident what they are saying. Okay, for Borel measurable sets in the interval 0, 1, okay, I can always find open and closed sets. Okay, which kind of approximate should be the Borel sets.
Sir, if it can extend for 0 to 1, it can be extended to 0 to 1.
Right.
I think we can extend it to 0 to 1 as well. Beyond 0 to 1 as well. Okay. Then I would like to write a theorem. It's called the Caratheodry extension theorem, which basically generalizes what we have done so far actually. Okay, so it generalizes it. Okay, so I'm not gonna prove it. The arguments are essentially same as, almost on the same line with a bit more abstraction, on the same lines as you did in case of the Caratheodry theorem. Okay. So here's the theorem. I mean, like one approach could be, and that's what I thought in the first place, that let's prove the Caratheodry extension theorem and get the Caratheodry theorem as a corollary of it. But then I thought that, okay, the Caratheodry theorem is a bit intuitive, you can make sense of it much easier than this actually. But extension theorem is also not, pretty much difficult. So, Caratheodry extension theorem. It's a bit more precise. So so previously on C, that was a collection of, maybe a sub-collection of, a collection of subsets of the given set X. We didn't assume the structure on it actually. We said that just C is a set and L is basically some kind of measure of it. Now I'm saying that suppose I have an A naught, okay. So I have a set X obviously, okay, and A naught is a collection of subsets of X, okay, but be an algebra. Okay, it's an algebra. Then I can prove a very nice result actually. Be algebra and what? And I have a notion of length on this algebra and what enter 0 to 1 plus infinity. Okay. Then I can define a map mu star from from all subsets of X in the 0 to plus infinity in following manner, that if I am computing the mu star of E, now guess what it would be? Then it would be the infimum, okay, of okay.
Sir, even interval cover you can.
It's like, okay, imagine that we can have several covers from where? AI runs from 1 to infinity,
Yeah, it goes.
and the AI is belongs to A naught, and I think AI is other this joint. Not necessarily.
No.
See here. Okay. And so you can have lots of covers in A naught for a key. Okay. And then do what? Then you take the infimum of such series as that. So I want to 1 to infinity, the length of AI is that. Okay. So in other words, if I want to compute the measure of, okay, not measure, but outer measure, I'm going to show that it's an outer measure of E, then see that E can be contained in which kind of, so in how many covers, not how many covers, but like, okay, if you have a cover, and we're going to have many covers for E, okay, and we should call it a cover actually, because I'm not, so when I'm saying cover, don't assume it in topological sense, please, okay. So E, so like this union is covering E, but there can be lots of such unions which are covering E, okay? And then compute their sizes actually. So this is nothing but just compute their sizes. And their sizes, so it's like the infimum of all such sizes would be the size of the E actually. Okay, so they're pretty much intuitive. For E subset of S. Okay? Then following is true. Number one, mu star is outer measure. So we have already proved it actually. We have already proved it. So the same proof that we did in Caratheodry theorem actually would work here as well. Okay. Why this would be the case? Because in Caratheodry theorem you had an assumption on A naught RBC that it's a subcollection but it contains empty set in X. But since A naught is an algebra, so it by default contains empty set in X. So you know.
So what is outer measure?
So we defined it once upon a time. Okay. So outer measure is something which is okay. So it's like a weaker notion than measure actually. Okay, it's a weaker notion than measure.
Yes.
So you can watch the next lectures. So mu star is an outer measure. It's almost like a measure, but
Countable
you know, but instead of some additivity, you have some additivity. In other words, when you compute the union, the measure of union of AIs, you don't get equality, but you get less than or equal to some I equals to mu star of here. The rest are almost same as okay. So mu star is outer measure. The second property is that if I take an element from the sigma algebra, okay. So if I take an element from the sigma algebra and I compute the mu star of such kind of an element, so what do you think what we're gonna get? So we also did similar kind of a thing in
length.
So you're going to get the length of the A. So in other words, so mu star is, so when you're having mu star, you haven't lost L actually, so it's already there.
We have extended.
Okay. So it's some kind of an extension. It's some kind of an extension. Okay. So what's the third property? The third property is that every A naught is mu star measurement. Okay, so this is also not something strong. We did it also. Okay. And the fourth property that it has is that if L is sigma finite, In other words, your length has this additional property of being sigma finite. Okay. You remember what's the meaning of sigma finite? Okay, I'll read. I'll define it. If your length is additionally sigma finite, then there exists a unique measure mu, okay, from the sigma algebra generated by your algebra into 0 plus infinity. Okay. Now, how I'm gonna get basically this mu? Obviously, I'm gonna get this mu by restricting the mu star onto this sigma algebra, which is generated by algebra. Okay. So, in some form, we have already done it. I mean, if you think about it, the only difference was so here's a question: if the collection of all open intervals are semi-open intervals, okay, would that be an algebra? Would that be an algebra? Could not be. So you have to add empty set and R into it.
Yes.
Okay. So you have to do additional things to turn it into an algebra. So in other words, this is slightly generalized than the previous thing that we have. But think about it. What we said that we have previously we had notion of length on C, we constructed outer measure, we constructed sigma algebra of mu star, okay, mu star, the sigma algebra which contains all mu star measurable sets, okay, which in this case becomes this actually. It's like a sigma algebra generated by roughly that algebra. So in other words, this thing is slightly generalizing your previous conclusion. And I can also treat the Lebesgue measure that we have M as an extension actually. As an extension of what? As an extension of the length, the notion of length that we have for the intervals.
सर ये आपकी सेंस में मतलब जब रियल लाइन की बात करते हैं तो वो नोशन ऑफ लेंथ का मतलब कॉन्सेप्ट आता है एंट्री की बात कर रहे हो तो मतलब व्हाट्स दैट
I mean, just think about it. I mean, the notion of length, if you are in R, the notion of length would be length actually. But if you are in, for example, R2, that would be area. In three-dimensional, it would be volume. Okay.
So we'll be constructing outer measure from
From the area and all. And that's what we're gonna do actually. So we're gonna do a whole chapter on product measures actually. Okay. How you can do the same thing in higher dimension. Okay. So in other words, this Caratheodry extension theorem, okay, it's not too much unexpected, it is expected actually. Okay, so this is as per our expectation. It's not something too strange. I'm not getting into the proof of it, you can read it. The arguments are pretty analog to what we have done previously, but they are a bit abstract because previously you didn't have any structure on C, while you have now a structure on C. Okay. So complete it for yourself, at least once in your life. Otherwise, keep this straight. Alright? So we're almost done with the chapter number 4. Now I'm gonna do what? I'm gonna talk about, let me see, some of the things that we have. Alright, so I'll also send you the exercise. Okay, in other words, which exercises you have to. I was waiting to complete it and then send you the things actually. Otherwise, if I'll just say that, okay, solve these exercises, otherwise, probably it will not make sense to you, but now hopefully you can do some of them. So, where I'm moving now, so I'm moving on chapter 8 from the past. Okay. Because chapter 8 actually. Because we have already done, so we have done almost everything from chapter 2 to chapter 7 actually. So there was fourth chapter missing, so we did it. So now I want to do what you call chapter 8, and I like to mention a result from chapter 9, okay, but without proof factor. Okay, and then we can move on to something else. Okay. So what's chapter 8? The chapter 8 is about the basic properties of the Lebesgue integrals. So we have already proved some of the properties like linearity and this and that. So we have proved lots of properties about the Lebesgue integrals. But I would like to show and see that there are some very important properties that all and know that. Right, so some properties of Lebesgue integral. I like to begin with a proposition which is also intuitive, and I think in Riemannian sense we did it also. The same property is also preserved here. So what does this say? So it says that suppose f is a real valued measurable. Okay, so suppose f is a real valued measurable function. Okay, I hope you remember that the meaning of measurable function. Okay. Function, and obviously I have an underlying space x, a, and mu, so it's there. And for every a in this sigma-algebra, we have integral of a over this set a d mu equal to 0. So f is kind of a strange function whose integral over on every measurable step is 0. Then we're gonna say that okay, there is something wrong with that. Not wrong, but there must be something obvious. So try to have a guess what it should be.
0.
F is 0. Not 0 always. Like, this is what is an important thing actually. Not 0. So you can have. Okay. So it's 0. So if this is the case, then f is 0 almost everywhere. It's almost everywhere. It doesn't mean that it's identically 0. Okay, so it could be non-zero on some points, but that must be negligible. So the collection of points where the f is not 0 has a measure 0 actually. So this is what that will like to show. So it generalizes your previous result that we might have done in functional analysis. That okay, if the Riemann integral is 0 in some sense and it is non-negative, then it must be 0. So this is pretty generalized statement, and it's true in all kind of measure space.
Sir, what is the precise definition for almost every SDA?
Okay, almost everywhere. I hope that I have defined it, but if I haven't defined it, I think I have defined it. So in other words, P is some property.
Yes, sir.
Okay. When I say that P it holds almost everywhere, okay, what it means that for the points for which P, which is some property, does not holds
0.
okay,
Measure of x is
the measure of such kind of points is 0.
same.
And if this property is a probabilistic property, okay, maybe something has to do with it, then you don't say almost everywhere, then you say almost surely.
Probability of such x is
So the probability of such x is happening is 0. So in other words, this property will hold with the probability 1 actually. This is what. So if I can have it. So consider an epsilon positive and consider a set A which consists of those points for which the property does not hold set. So in other words,
Non-zero.
consists of x such that f of x is bigger than epsilon by choosing epsilon. It's almost the same way to say the same thing. And I want to show that the measure of this set is 0. Then f would be so. So what would be the true thing? The complement of this set. The complement would be that less than or equal to epsilon. You can make it epsilon arbitrarily small actually, and hence eventually we can show that f is there. Okay, so I have an epsilon and I have a set, which consists of those points obviously from x, okay, for which the f of x is bigger than epsilon. And then let's play with the set. Here's the question. Why does this set belong to the sigma-algebra?
F is measurable.
Because f is measurable. Okay? So this guy belongs to A and D.
Sir, what about the negative values of f? So we are proving it for positive values.
So I can argue similarly about negative. Okay? So in other words, if I show that for measure of such kind of thing is 0, and then I can argue something similar, actually, less than minus epsilon, and then I can also show that. Okay? So I'll do the both, or at least I'll do one way and you can do that. Alright? Because his point is right actually, that f could be anything. It's very valid. So why do you think that it is positive? Like this will be true for the positive thing, but so I know that since this is measurable and this f has a property that whenever a set is measurable, its integral is 0, that means that f must be 0 in this case. Okay. But on such a set, f is bigger than epsilon. Now I would say that okay, this must be bigger than or equal to dp. Agree? F is bigger than or equal to some number, then the integral would be also. Integral will be also. So this means that this is same as epsilon times
measure of a.
mu of a.
Epsilon is not direction measure of a.
So we're saying that if